let's examine ligand field splitting further. Now, there's really two cases that we can break this down into. There's high spin and low spin. Sometimes high spin is also called low field, and sometimes low spin is called high field. Now, the spin is when we have a number of unpaired electrons, and that will lead to a higher magnetic interaction, and so that's why we call it high spin. And the spin of an electron is whether it's up or down, and so if we have a lot of unpaired electrons, we'll have a high spin. Now, conversely, if we have a lot of paired electrons, we'll have a lower spin situation. This is also called low field and high field. It can sometimes be a little bit weird that these are exact opposite. That's high spin, which is caused by a low field. But here's the explanation. In a low field situation, we have a very small amount of sigma donation going into the metal. And we may even have pi donation. Well, what's the effect of both of these things? Well, if we have a small amount of sigma donation, then the Eg orbital is not pushed up as much as it could be. Remember that the Eg orbital is made up of the dz squared and the x squared minus y squared orbitals. Those are situated on the coordinate axes, and that's where the ligands go. So if there's very little electron density flowing from the ligands into the metal, the effect on the Eg orbital will be less. Conversely, if there is a large sigma donation, then there'll be a much larger gap in between the T2G and the Eg orbital. These will get pushed up quite a bit more than these did. These just got pushed up a little bit. Now, I also said something about pi donation and pi acceptor. Well, if we have a pi donation, that will increase the level of the T2G orbitals, because the T2G orbitals are in between the coordinate axes, and they are lined up quite nicely for p orbitals that are on the ligand to interact with those orbitals that are in between the axes. And so that can, if they're donating electron density in there, that can raise the T2G orbital as well. So it's not just how much electron density we're feeding into the metal from the sigma or the bonding orbital, it's also, we can have pi donation. And this is why ligands such as halogens, chlorine, bromine, iodine, and a little bit of fluorine have small fields or high spins, because they don't donate very well in the sigma interaction, and they do have some pi donation. Remember, they have a lot of lone pair electrons around the ligand. The ligand already comes with a full octet. Like bromine minus, right, has 8 electrons. So all of its orbitals are full, and so it can do some sigma donation, and it can also do pi donation. But again, we're talking about fairly electronegative elements, and so the effect is lessened. Now, conversely, we can have very large pi donation, something that is a good Lewis base. So, like hydroxide or ammonia. Those are very good sigma donors. They feed a lot of electron density into the metal. We can even go a step further and have ligands that are capable of accepting electron donation from the metal into pi orbitals. And often this would take the form of an anti-bonding pi orbital. So something like a carbon monoxide ligand or a cyanide ligand is capable of accepting pi electrons back into its antibonding orbital, which will weaken the bond within the ligand, but it will strengthen the bond between the ligand and the metal, and it will lower this orbital's energy. So this energy will get lower, and this one will get higher because of the sigma donation. So this will push this one up, this one will come down. The net effect, and what we actually are looking at, is that the energy difference between the T2G and the EG orbital will get a lot larger. Now, let's explore what happens when we start populating these orbitals with electrons. So, if we start out with one electron in each, oh, by the way, before we put any electrons in, let's talk about what happens when we have no electrons in the orbitals. When we have 0 electrons in the orbitals, the compounds will be white, such as titanium 4, right? Titanium 4 has no electrons in the T2G orbital or EG orbital. And so since there's no electrons there, there's no possibility of an electron transferring between these two. They don't have color. All right, so let's put an electron in. And this would be 1d electron. Now, you'll notice that in both cases, they're the same configuration. There's 1 electron in each thing right here. Let's try 2. Now, we're putting the electron in the next orbital over because we want to avoid the electron pairing energy. It takes energy to put an electron in the same orbital as its neighbor. They're both negatively charged, and so they will repel each other. Fortunately, so far, we're able to put an electron in its own separate orbital. Same story when we get to D3. Okay. Now, when we get to D4, we have a choice. Do we put the electron in this orbital next to another, or do we put it up here? Well, again, there's a penalty for putting an electron in next to another electron. And if that penalty is less than the energy required to put it in the next orbital up, the electron will go up here. And since these orbitals are not very far apart from each other, that electron goes up here. And in this case, we'll have 4 unpaired electrons. And we can measure the number of unpaired electrons something has using magnetic susceptibility. And it's possible to do that with a nuclear magnetic resonance instrument, but it's also possible to do it with some very strong neodymium magnets and an analytical balance. So it's possible to do it both ways. Now, if we look over here, we have the same choice. We can either pair up an electron or we can put it on this higher energy orbital. However, you'll notice that the energy gap between these two is significantly larger than it is over here. And in this case, it's large enough that the energy to put the other electron next to another one is less than putting the energy up here. So it goes down here. And this one only has 2 unpaired electrons, hence the name low spin. The spin is coming from unpaired electrons. This one has 4, that one only has 2. Let's look at the case of 5 electrons. So if we have 5, then we see that our high spin case has 5 unpaired electrons, and our low spin case has 1 unpaired electron. Again, this has significantly less unpaired electrons than our high spin case does. Now, let's start with 6. Now, when we have 6, all of these electrons or orbitals have one electron in them. So we'll just have to start pairing them up. And if we have a choice, we'll pair it up on the lower energy orbital. Down here, we can still locate that electron in the lower energy orbital. And now we have 4 unpaired electrons in the D6 high spin case, and we have 0 unpaired electrons in the D6 low spin case. Now let's see what happens with 7. When we add 7 electrons in, we'll have 3 unpaired electrons in the high spin case. And in this case, our T2G orbital is full, so we'll have to start putting electrons in the EG orbital. And we have 1 unpaired electron up there. Well, and we have 3 here. Now, when we get to D8 and beyond, D8, 9, and 10, both the high spin and the low spin cases have the same number of unpaired electrons. I'll demonstrate that. D8 is like this, and you'll notice that we have a fully populated T2G orbital down here, and then we have a half-filled EG orbital up there. And then if we go and continue on to D9, very similar, 1 unpaired electron in both, and D10, all the orbitals are full, and we have no unpaired electrons. So really, the energy or the differences that we see between high spin and low spin or low field, high field cases only occurs from D4 to D7. So 4 electrons in the d orbitals, 5, 6, and 7. The other configurations are the same, whether it's high spin or low spin, because there's 3 spots, and so once we fill up the lower orbital, we'll start to see some differences between them.